Our next example subsystem is that for an elevator. Again, this is just for an example. It's not going to work with any physical elevator mechanism without changes, but it does illustrate several interesting features and best practices, and is based on and derived from Husky Robotics elevator in 2025 for Reefscape. Again, topics that we've touched on before, we'll skim over a little bit quickly, and we'll focus on things that are kind of unique to this example subsystem. Specifically, we'll focus on how we can use a filter to determine when the elevator is being jammed. A similar approach could be used to determine when a game piece has been shot or collected as well. And we'll see that we have a slightly different simulation class that we use for the elevator modeling. But much of the other stuff we will kind of gloss over because it's similar to what we saw in the example subsystems for the shooter and the arm. All right, so here's our elevator. Again, the reference the IO and the inputs that we're familiar with. Here's an alert that we'll use when we detect that the elevator is jammed. That's going to use that filter. Here's the linear filter that we create. It's a single pole IIR filter with this time constant and period to get the behavior that we're looking for. We're going to feed values into this jam filter and to determine if the elevator has been jammed. When we get to the code that uses that, we'll talk more about why the filter plays a useful role. We have tunables for testing, like we saw elsewhere, where we can command a specific voltage just to make the elevator move up and down. Great when we're first bringing the mechanism online, as well as to command a specific position of the elevator, which again, useful when we're testing the mechanism, but also useful when we're characterizing it for performance on the field. For example, maybe we want to adjust the elevator, determine specific positions for scoring at different levels of the branch on the reef. SysID routine, similar to what we saw with the arm. We're overriding some values here because, again, like the arm, the elevator has a limited range of motion, and so we want to, within that limited range of motion, get the best data we can that we can feed to SysID. So as a result, we increase the ramp rate so that we move through a greater range of voltages before we run out of room on the elevator, and then also changing the step voltage as well. All right. So when we construct a new elevator, grab the reference.io object, we zero it out. Since it does assume that the elevator starts in the down position. If it doesn't, then that's going to be problematic. There could be, and there was a point in the 2025 season where we had code that would re-zero the elevator when it got all the way to the bottom. So basically we'd stall it against the bottom hard stop. Once it's stalled, we'd zero it and we go on to the next thing. And then over time we determined that wasn't actually needed. So we got rid of that. But that is certainly an option if the mechanism warrants it. Here is where we add our elevator voltage to the SysID routine chooser. And here is where we add our system check command to the fault reporter. So just to see what this one does, here we're just going to set the elevator to a bottom, middle, and top position. And for each one, we'll tell it to go to that position. We'll check if it's at that position with a certain timeout. So slightly different approach here than we saw with the shooter and the arm. Here, we're just waiting until it's at position with a certain timeout. So if we don't get there within a second, then that's a problem. And so we'll wait until it's at position and then we'll check the position. So a little bit different approach than we saw with the other two. And again, if we're not at the right position, we generate a fault, say, hey, it should be here, but it's here. Cool. So let's look at what we do inside of periodic. As always, we update the inputs, we process the inputs. Sometimes subsystems may need to log some extra information um, beyond what is in the IOInputs class. Here we're going to log the target position, but periodic is a good place to do that as well. Commands, again, are going to control the elevator, but there's other things that need to be done in periodic in the case of the elevator besides just dealing with the inputs. And that is to see if the elevator is jammed. And so the way we do this is we decide the elevator is jammed if the current exceeds a certain threshold for a certain period of time. Um, we can't just say if it exceeds a certain threshold because when the elevator starts moving, it draws a lot of current because those motors are at rest. We have to get them going. Big current could draw at the start. Um, but if the elevator is consistently at a high current, then that's not to be expected. And so here's the approach that we take here. So we use that filter that we created up above, and we pass in the stator current. Um, and then if that filter returns a value that's greater than our jammed current, which is 59 amps, I think our current limit is set to 60. We'll look at the constants in a moment. Then we're like, ooh, the elevator is jammed. We should do something about it. Now, we could simply tell the elevator to stop right here, but that wouldn't really work or have the desired effect because, again, the elevator is controlled through various commands, and there could be commands running right now that are telling the elevator to move to a certain position. So if we tell the elevator, if we set the voltage of the elevator to 0, then the very next cycle, that command, which is still running, is going to try to tell it to move again, and that's not what we want. So instead, what we do is we schedule a command to run in the next cycle. And that has the effect of it will because it requires the elevator, it will interrupt other commands that are running that are using the elevator so that they stop trying to command the elevator. And instead, this command will run, which will set the motor voltage to 0. It will have the LEDs indicate that the elevator is jammed, so the driver and operator know something has gone wrong here. Um, and so that command will get scheduled. We also set an alert, so it shows up in Elastic that the elevator has been jammed. And then it's up to the driver and the operator to use manual controls to figure out why the elevator is jammed. Maybe a game piece got stuck in there weird or something. Manually move the elevator, get that game piece out of the way. On we go. All right. So this is kind of a neat example of how we can do something like that and highlights the importance of actually scheduling a command versus just telling the elevator voltage to be 0, for example. Similar code here for when we're testing. And again, the log tracer record like we always have for performance profiling. All right. This is modeled off of like Reefscape. So we have here, let's look at elevator constants while we're here. We have the CAN IDs of the lead and the follower motor. Oh, so one of the things we're going to get to see here is how to do a lead and a follower. With CTRE, we have two motors here controlling the elevator. They're both part of the same gearbox, however. We have our PID values. We have our feed forward values. Again, these came from SysID. We're using Motion Magic Expo, so we have our KV and KA and cruise velocity for that. Other things here in terms of inverted, the circumference of the pulley. This is a belt-driven elevator, some of the gear ratios, the mass of the elevator used for simulation, tolerance in terms of being at position, different voltages for going up or down. Here's the limit for when we're decide we're jammed, and the limit, just the general current limit in general. An enumeration of different positions, just bottom, middle, top. They could be different branches if it was Reefscape, for example. And then like heights corresponding to those that we have determined empirically. So we have a method that will convert from that positions enumeration, just like a different reef branch, to the corresponding height as distances. We have a method to check if we're at the position to make sure we're there within a certain amount. I suppose there is an opportunity here to use a debouncer as well, like we saw with the arm and the shooter. That would be cool. We saw our systems check command earlier. Methods here to go to a given position. Where we convert that position to a distance. Accessor to get the position. Method to raise the elevator slowly, lower it slowly. So maybe that's for the manual control. Stopping the elevator, zeroing the elevator's position out, things like that. Great. All right, let's look at the IO class. So here's our elevator IO interface. Here's the inputs class. Most of these properties are duplicated for both the lead and the follower motor: voltage, stator current, supply current, the temperature. There you go. The velocity, again, just of the lead, closed loop error, closed loop reference, position inches, position rotations. Sometimes it's helpful to save us the unit conversion and just log both of those. Is relatively straightforward. We have the updates input method, of course, and then there's three methods that the class that implements the IO interface will have to do: set position, zero position, set motor, voltage. So let's look at elevator IO Talon FX. We have the lead and the follower. We will use Motion Magic Expo voltage, but also voltage out for direct control of the elevator. We have some alerts here for the configurations. Our status signals that we care about. The debouncer for connected, tunables for the PID and the feed forward values, and then Motion Magic values. Here, we're using elevator system sim. We'll dive into that a little bit more when we construct that object. So we make our lead Talon FX, we make our follower Talon FX. We get all the status signals that we want. We register all those signals. Again, we won't call refresh anywhere in this class. We create our control objects for Motion Magic Expo and for voltage. Configure the lead and the follower. Let's actually look at that. So configuring the motor lead, current limits, sensor to mechanism ratio, inverted, neutral mode, PID, feed forward stuff. We set the gravity type to elevator static. That's important because it's just going straight up and down. Motion magic things. Here's a cool feature. If we want to zero the elevator, by default, if we just call set position 0, that does a config call through Phoenix 6, and config calls can be a bit of a performance hit. So instead, what we do is we set up that we are going to have an external hardware limit switch that would be used to zero it. So we configure that we are enabling the auto set position on this external hardware limit switch. And when it's triggered, the position will be 0, and it's enabled. And you'll see where we use this then to very efficiently reset the position to 0 without taking that performance hit. We use Phoenix 6 util to apply and check the configuration as always. We register the hardware as always. Configuring the follower, we set the neutral mode. We set the same current limits. It was recommended, I believe CTRE recommends that you set current limits on the follower as well as the lead, so we do so. We apply and check the configuration of the follower and still register the hardware with fault reporter as well. Then, after we've configured each of the motors individually, we come back here and we set the control on the follower to a new follower based on the device ID of the lead, and we say it opposes the direction. Again, this is just an example, and it depends upon your individual mechanism, but the way this mechanism is designed and the way the gearbox is built, the lead and the follower need to rotate in opposite directions to make the elevator go up or down. Here's our simulation object for the elevator. This is the third type of system simulation that 3061 lib supports. Very similar to the other two that we saw. To dive into it into a little bit more details, quick look at it. A bunch of things in terms of like the gear ratios, what's the mass of the carriage, the pulley radius, min and max height, starting height, all these things. There is an actual WPI lib elevator sim, so we leverage that, which is great. Like we saw with the arm, we are using a logged mechanism 2D here, and we have a base for the elevator, and then we have the elevator extension itself, which will move up and down. So in Advantage Scope, we can visually see the elevator moving up and down, which is helpful. And then again, we have our update sim method, just like we do for the other system sim objects, where we do the necessary things to bridge communication between CTREs, sim state, and our physics model, in this case, the elevator sim from WPI lib. So very similar there. And then we update the mechanism 2D as well, so we can visually see the changes. All right, update inputs. We use the debouncer to determine if both the lead and the follower are still connected. We update all the status signals. Only if we're in tuning mode do we directly get the closed loop error and closed loop reference. Here's an example where we get the elevator position status signal, which will be rotations, but we convert it to inches just because it's convenient. Doesn't take that much long. Again, with our tunables, if any of these tunables have changed, we need to update our configuration appropriately. So that's what all of this does. And then the very last thing we do, as always, is to invoke the update sim method on our system sim object. Other methods that we said we had to implement was a set motor voltage, which we do here. You'll notice this is a little bit different than we've seen before because we're used to seeing just set control and then like lead voltage request with output and the voltage. Here we have with limit reverse motion false. Um, this deals with that external hardware limit switch. So this is just saying like that limit switch is not triggered, so it's not going to zero that position. However, when the zero position method is called, we'll do a set control with the lead voltage request, and then we'll use the with limit reverse motion and set it to true, meaning the external hardware limit switch is triggered. There isn't one, but we're pretending one is triggered because we do want the position to be set to zero. And then we just say with output zero because we don't actually need the elevator to move. We just want to zero the position. If set position is called to a given position, we then use the lead position request instead with position and do the position. Now note that the position is like done in terms of inches from an elevator perspective, like 12 inches up, 24 inches up, whatever. This is used to, this wants it in terms of rotations. And so therefore we need to divide it by the circumference of the pulley in inches. So, all right, there's our configure commands, and that is it. So there's an example of what a elevator subsystem looks like in 3061 lib.